Okay, the masked professor is on the air. And fans of the show may notice I have a new and improved mask. I asked a friend what they thought, and they said, too Jewish. All right, well, anyway. So, we will be skipping chapter 23 about CAD/CAM for the moment, and jumping into chapter 24, which is process planning and concurrent engineering. All right, so the sections in this chapter are process planning, computer-aided process planning, concurrent engineering and design for manufacturing, and advanced manufacturing planning. Process planning we define as determining the most appropriate manufacturing processes and the sequence in which they should be performed to produce a given part or product specified by design engineering. The limitations that are imposed by the available processing equipment and the productive capacity of the factory have to be considered in the process planning process. Any parts or sub-assemblies that can't be made internally, we will have to purchase from external suppliers. So who does the process planning? Usually I'm sorry? The first one? I'm sorry, was that a question? Or that was a random? In Brooklyn, okay, I'm not sure what you're saying. If you have a question, go ahead and put it in chat, and let me see it that way, since we seem to be having some difficulty communicating. All right, so ordinarily, process planning is done by manufacturing engineers. They should be familiar with the processes in our facility and are able to read engineering drawings. Although more and more, we want everyone who works with us to be able to read the engineering drawings. Based on their knowledge, skill, and experience, they develop the processing steps in the most logical sequence that is required to make each part. Now, in the most logical sequence may just be from their point of view. And as I've discussed before, very often the way to improve a process is to come in and look at that sequence and see if there are improvements that can be done based pretty much just on the sequence. Some details we delegate to specialists such as tool designers. But overall, our manufacturing or industrial engineering department is going to have responsibility for our process planning process. Okay, that's interesting. Can you still see the presentation on the screen? All right. All right. So the details when we're talking about process planning, first of all, we have to interpret the design drawings. We have to take the part or the product design and analyze that to begin the process planning procedure. So we have to understand what are the starting materials, what are the dimensions, and what are the tolerances. So all of those will make a difference as far as what processes we use. So when we think of our process with the sequence, our process plan needs to describe all the processing steps that we are going to use to produce the work unit and the order in which they're going to be performed. So another thing that we need to be aware of in our process planning is equipment selection. Mostly we are going to try to develop a process plan that utilizes the existing plant equipment. Otherwise, we're going to have to look at either purchasing the parts or purchasing the equipment to make the parts that we don't have now. When we talk about tools, dies, molds, fixtures, and gauges, that design of special tooling we usually delegate to the tool design group. And the fabrication of those is accomplished by the tool room. Now, depending on the product that we're talking about, they may actually provide the design of the special tools needed. For example, when I was working at the Corpus Christi Army Depot, inside the technical manuals or the technical orders, they would provide the design for specialty tools for different parts of the helicopters. So, free that memory and get on with it. So, another thing is we have to do methods analysis. That is looking at the hand and body motions, the workplace layout, the small tools, or hoists for lifting heavy parts. Our methods are going to have to be specified for manual operations like assembly and the manual portions of the machine cycles, loading and unloading a machine, or securing things in a jig or a fixture. We want to set work standards, so setting those time standards using work measurement techniques. And we want to see what we need to do as far as cutting tools and cutting conditions for the machining operations. One of the things that's very important to know is how many times can a cutting tool be used before it needs to be sharpened or replaced.
Right. I think that.
So our process planning for parts, the processes that we need when we manufacture any given part are determined by the material out of which the part is made and the design of the part itself. So the material is selected by the product designer based on functional requirements. When that material has been selected, that narrows down our possible processes that we can use to shape it. One thing that we need to remember is that very often designers specify things too tightly. They'll specify a very exotic material when something more ordinary and cheap would work. Or they'll specify extremely high tolerance when in fact a lower tolerance would be acceptable. So anytime that it looks like it's going to be very hard to make processes that will fulfill the design, we need to go back to the designer and say, all right, does it really need to be like this? Does it have to be titanium, or would ordinary steel do? Do we really have to have tolerances that are to the micrometer, etc.? All right, so a typical processing sequence is going to have a basic process that gets it to the basic shape that we want, one or more secondary processes, and then we may have operations that enhance physical properties. After that, we will go to finishing processes, such as surface finishing or coating, electroplating, etc. All right, so here we're seeing the typical processing sequence, and this is the typical sequence of processes required in part fabrication. So we start with a raw material. We have a basic process that gets it somewhat in the shape that we want. A secondary process that further enhances that shape. That may go to a property enhancing process which may end up being a loop with the secondary process until we get the shape in the proper shape. And then we go to our finishing operations and we have a finished part. All right, well, obviously this is a very crude and not necessarily accurate depiction of how we would get to where we need to be. So our basic process is going to establish our initial geometry of our work part. So for example, that might be metal casting, it might be forging, it might be sheet metal rolling. The secondary processes, well, most of the time that starting geometry will have to be modified or refined by a series of secondary processes. So we have cast or forged our part, then we get it closer to the finished dimensions in our secondary process until we get to our final geometry. So examples of this might be machining or stamping. Then we have property enhancement and finishing operations. Okay, so operations to enhance the properties might be heat treatment operations. Those can be used to strengthen the metal components, but the parts may not need property enhancing steps. It may be that those are not required at all. So then we have finishing operations, which should be the final operations in the sequence. They're talking about providing a coating on the surface, either with electroplating or painting. Powder coating is now a very popular operation. All right, so these are examples of some typical process sequences. The basic process might be sand casting, the secondary process machining, property enhancing might be treating, and then the finishing operation is painting. Another example, the basic process might be rolling a sheet of metal. Secondary process might be blanking or bending the metal. No property enhancing, and then plating. Similarly, it might be forging, machining, no property enhancement, and painting. The basic process might be extrusion, cutting that to length, no property enhancing, and anodizing. They're noting that that would be particularly for aluminum. And then the last example is casting of glass, pressing or blowing it, annealing it, and then a chemical etch on the glass. Okay, well, these are typical process sequences. By no means is this all-inclusive. All right, so our process planning begins after the basic process gives us the initial part sheet. So, an example might be that machine parts start as bar stock or castings or forgings. And sometimes these processes are external to the entire fabricating process within our facility. Stampings may begin as sheet metal coils or strips that we're purchasing from the mill. So there's not but again, the basic process is to get us close to the initial geometry. So very often, these are supplied by external suppliers, and then we do more secondary processes and finishing work at our facility. All right, so route sheets. I've talked about route sheets before in this class, and they are very important to get our parts from A to B to C to D, et cetera, et cetera. So it's a document that specifies the details of our process plan. The route sheet is to the process planner what the engineering drawing is to the product designer. Okay, why not? The route sheet should include all manufacturing operations to be performed on the work part, listed in the order in which they are to be performed. All right, so here we see what is intended to be a typical route sheet. All right, so this is at the XYZ Machine Shop Incorporated. We have a part number 081099. It's a generator shaft. The author has put himself down as the planner, checked by N needed. And who says these textbook writers don't have any sense of humor? It specifies the material the parts to be made out of, the stock size that we start with, and then we have the number of the operation description, the department, the machine that it needs to be done on, the tooling needed, the setup time, and the standard time to produce the part. So in this case, operation number 10 is face the end, rough turn it to 52 millimeter diameter, and then finish turn to 50 millimeter diameter, face and turn shoulder to 42 millimeters diameter and 15 millimeters length. All right, so it specifies the department, the machine, tooling, the setup time is an hour, and the standard time is 5.2 minutes to do that. Operation number 20, reverse the end, face the end to 200 millimeters length, rough turn to 52 millimeters length, finish turn to 50 millimeters diameter. 52 millimeter diameter, I should have said. All right, so that's on the lathe. It's still on the same machine. The tooling is the same, the setup time, and the standard time to perform the operation. 3, operation number 30, drill 4 radial holes, 7.5 millimeters diameter for the holes. We use a drill, it's D09, the tooling is a J555, setup time and standard time. Right, so we can see, all right, so it's giving us a detailed look at what each operation should do and accomplish. When we talk about the process planning for assemblies, for a single station, our documentation has a list of assembly steps in the order in which they must be accomplished. So for assembly line production, our process planning consists of line balancing, making sure that our work elements are allocated to the different stations along the line so that everyone has a more or less equal amount of work. So, as with any process planning for individual parts, any tools, any fixtures, any jigs needed to accomplish the given assembly task must be decided, and our workplace layout must be designed. All right, well, one of the big questions always when we're talking about process planning is the make or buy decision. When we think about our parts, there are some parts we're going to go ahead and make in-house, and other parts we're going to buy. So, whether we should purchase that from an outside vendor or make it internally, well, pretty much everyone purchases their starting materials from suppliers. Not too many use the old Henry Ford idea that iron ore is dug up by Ford equipment at Ford mines, loaded onto Ford ships, shipped to Detroit to be smelted and turned into iron at a Ford steel works, and then turned into a Ford car by Ford machines. So very few product operations are vertically integrated like that from raw materials to the finished product anymore. So, thinking that the company purchases some or all of the materials, the raw materials we need, we need to question whether the company should purchase the parts that would otherwise be made in its own factory. So, when we answer the make or buy question and make the make or buy decision, we do that for every component that goes into our products. Now, some things we may say, you know what, it's not worth it to have to make. So very often with bolts and screws, the decision is just go ahead and buy them. It's not worth it, our time, to have to worry about making those. right? But as the parts become more complex, the make or buy decision also becomes more complex. All right, so here we have an example of the make or buy decision. So we are given a quoted part price from a vendor as $20 per unit when we order 100 units at a time. The same part made in our home factory or facility would cost $28. So the cost breakdown on our make alternative, the unit material cost, $8 per unit, direct labor is $6 per unit. Our labor overhead at 150% is $9 per unit. Equipment fixed cost is $5 per unit for a total of $28 per unit. Now, one thing that is often left out, and I'm very glad they put it in to this example, is our labor overhead. It's not just the cost of labor. There is a cost to having that labor available. When we think in terms of having people working, we should think that the overhead on that labor is going to be at least as much as the person is getting paid. In this case, they're putting it at 150% of what that person is getting paid, right? Because that is going to go into things like insurance, taxes, all kinds of little business things that we don't necessarily think about when we think about our make or buy decision. So, right now we have a vendor will make that part at $20 a unit is if we order 100 units. We can make that part at $28 a unit. So should we buy that or make it in-house? All right. Now the vendor's quote seems to say, hey, go ahead and buy it because we already are talking that it costs $8 more to make it in the factory. But the equipment cost of $5 is already a sunk cost. When we got that equipment, we had to invest a certain amount. So if we don't use the equipment, the cost for that continues even when we're not using the equipment. Something that hasn't been initially considered in the make or buy decision is the overhead cost, which is $9. So in this case, they're saying that's the factory floor space, the indirect labor, and other costs that are going to continue even if the part is bought, which means that when we add the $5 plus the $9 to our $20 cost per unit when we buy 100 units, then the real cost becomes $34 per unit. Okay, so when we think about the make or buy decision, we have to make sure that we are properly accounting for all the costs that go into that. Now, why would that buy decision be a good economic decision? If that equipment is going to be used to produce other components where it makes more sense to make it in our factory than it does to buy it from a vendor, then that buy decision at $20 per unit per 100 units makes good sense. Otherwise, if the machine is just going to be idle, then no, not so much. All right, so one thing that has come into use in recent years is computer-aided process planning software. So people are interested in automating that process planning function so that more of it can be done by computers. Now there are some different reasons for this. One thing is, if we can get computers to take this over, then that is going to be cheaper, almost certainly, than having to have experienced people who are doing the process planning. And the people that have experience and knowledge are retiring. They're not necessarily being replaced by people that have equivalent experience and knowledge. So they're looking for an alternative approach to the process planning process. And computer-aided process planning is the alternative they're looking at. So what are the benefits of using that computer-aided process planning? Well, one thing is we have process rationalization and standardization. The computer-aided process planning will give us more logical and consistent process plans than traditional process planning. All to the good. This means that we can increase the productivity of the process planners that we have. There are some things that machines won't be able to decide or be able to understand at this point. Having a computer-aided process planning will reduce the lead time to prepare those process plans. Improve the legibility over manually written route sheets. I actually assume that route sheets are put together on the computer, but maybe that's just me. We can incorporate other application programs so that we are interfacing with other programs like cost estimating, work standards, and numerical control part programming. So our computer-aided process planning systems use one of two approaches. One is a retrieval system, and the other is a generative system. A retrieval type of computer-aided process planning system. Well, first of all, we base that on group technology and our parts classification and coding. So we have a standard process plan in the computer files for every part code number. Part number code, number code part. Those standard plans are going to be based on our current part routings that we're using in the factory, or on an ideal plan prepared for each family. Right? New parts will be introduced. So for each new part, our standard plan will be edited if we need modifications. So these are known as variant computer-aided processing planning systems. All right, so in this case, we see a flow chart. We have a new part design. We derive the group technology code number for the part. We search the part family file for the group technology code number. That goes into the part family file, and man, the way they put this together is bothering me. Right? That then means there's a standard process plan file. We retrieve that standard process plan, edit the existing plan or write a new plan, use a process plan formatter that may feed into other application programs, and then we have our process plan or route sheet. In the preparatory stage, so this starts way before we have any of this, we select our coding system and form part families, prepare standard process plans for part families. Okay, so that, it seems like, shouldn't have been part of this diagram. All right, so if our file doesn't contain a standard process plan for a given code number, we may search the file for a similar code number. So when we edit an existing process plan or start from scratch, we're going to develop a new process plan that becomes the standard plan for the new part code. Okay, so really, a lot of this is just using the enormous and fast memory aspect of the computers. Then our final step is our process plan format. The formatter may, again, call on other application programs that determine the cutting conditions, calculate the standard times, or give us cost estimates. So a generative computer-aided process plan system. Rather than we're retrieving and editing an existing plan from a database, a new process plan is created using systematic procedures that might be applied by a human planner. So if we have a fully generative computer-aided process plan system, our process sequence is planned and without any human assistance and without any predefined standard plans. So designing that generative computer-aided process plan system is a problem in creating an expert system. An expert system is a computer program capable of solving complex problems that normally require a human with years of education and experience. The components that go into an expert system, first of all, there's the knowledge base. We must have the technical knowledge of manufacturing and logic that is used by process planners. That has to be captured and coded in a computer program. Then we have to have a computer-compatible part description. That description has to have all the pertinent data that are going to be needed to plan the process sequence. Then we're going to need an inference engine. This is an algorithm that applies the planning logic and process knowledge contained in the knowledge base to a given part description. All right, so when we have product development, we have two possible approaches. One is the traditional product development cycle. We have some people design a product, they throw it over the wall to the manufacturing, engineering, and process planning people, and then it goes into production and assembly. So that gives us, though, a very long time from the time we begin designing the product until we actually are making it. B, we use concurrent engineering to develop products. And that is where our product design is informed by sales and marketing, by quality engineering, by vendors, by the manufacturing and process planning guys, and production and assembly. That shortens the time tremendously to design and build the product. All right, so our traditional approach, we separates our design and manufacturing engineering. That product design group develops the new design, and a lot of times they pay no attention to our manufacturing capability or sometimes even common sense. So there's no interaction or little interaction between the design engineers and the manufacturing engineers, which is too bad because the manufacturing engineers might be able to give good advice on how do we make this. Concurrent engineering is a method that we use now where we get everybody in on the product design at once so that we not only shorten the time, but we eliminate problems within the design process. So our manufacturing engineering group is involved early in the product development cycle. We also have many other functions involved, such as the field service technicians, quality engineering, the manufacturing departments, the vendors, and depending on the product, the customers as well. All of these functions working together can make our product design that performs well, does its functions, but it's also manufacturable, assemblable, inspectable, testable, serviceable, maintainable, free of defectables, free of defects, and safe. Because everyone's viewpoint has been considered at the beginning, so that helps us to design a product with high quality, and that will give us customer satisfaction. Getting everyone involved early shortens the product development cycle time. Design for manufacturing and design for assembly are ideas that have begun to gain currency in recent years. It was eventually recognized that 70% of our life cycle cost is determined by the basic decisions made during product design. So those decisions could be materials for each part, the part geometry, the tolerances, how the parts are organized into sub-assemblies and assembly methods. Once all of these decisions have been made, though, our ability to reduce the manufacturing cost becomes very limited. So, how does our design affect the process planning? The example they give is if the product engineer designs an aluminum sand casting with features that can be achieved only by machining, then our process planner must specify using sand casting followed by the necessary machining operations. But the manufacturing engineer might tell the designer that a plastic molded part would be superior. So, we want the manufacturing engineer to have the opportunity to advise the design engineer as we are creating the product design. One thing that I noticed particularly about this chapter is the author never talks about 3D printing. Now, 3D printing does have its drawbacks. For example, compared to some other kinds of manufacturing, it tends to be slow. However, we also know that 3D printing can make things that essentially can't be made in any other way. Careful design can mean that a 3D assembly is printed that is already assembled and ready to operate. All right, so our design for manufacturing and assembly means that when we design the product, we are considering how is it going to be manufactured and how is it going to be assembled in practice. So, our design for manufacturing and assembly is going to include organizational changes and what are the design principles and guidelines that are going to be implemented during the product design so that it is designed for the manufacturing and assembly processes. So the organizational changes required by design for manufacturing and assembly, we're going to have closer interaction between the design and the manufacturing personnel. Very often we do this by forming design project teams that have project designers, manufacturing engineers, and the other specialties needed. In some companies, our design engineers have to begin or at least spend some time in the manufacturing processes to find out what the problems are when we make things. I noticed that they talk about the design for manufacturing and assembly principles and guidelines without actually bringing up any of the principles and guidelines. But we just certainly have these principles and guidelines that tell us how to design a given product so that it has a maximum manufacturability. Some of these principles and guidelines are going to be universal. In other words, they're going to be rules of thumb we can apply to pretty much any product design. The design of manufacturing and assembly is also going to have principles that are specific to manufacturing. So, some examples of those principles: minimize the number of components in the product, right? This is always good design. The fewer things that go into it, the fewer things that can go wrong with it. Use standard commercially available components whenever possible, or COTS, commercial off-the-shelf hardware. Use common parts across product lines. We don't want to be making essentially what is the same part but has to have different features for different products. We want to use the same part. Design parts with tolerances that are within the process capability. This is one where a lot of designers fall down. They start specifying too fine a tolerance, when in fact a looser tolerance would be perfectly okay. Design the product for foolproof assembly. What can go wrong will go wrong, as the old adage reminds us. Use modular design. In other words, if we're able to take part of the assembly apart while other parts of it stay together, that's going to make it easier. Shape the parts and products for ease of packaging. That's a very smart one. And eliminate or reduce the adjustments needed for manufacturing and assembly. Some other kinds of product design objectives. Design for quality. Think in terms of principles and the procedures that will give us the highest possible quality in having those designed into the product. Design for the product cost, so that we are specifically identifying how the design decisions affect the product costs and develop the ways to reduce that cost through our design. Design for the life cycle. In that case, we are considering what the costs are that are associated with the reliability, maintainability, serviceability, which could be a big portion of the cost of the product. All right, so one of the things we want to think about is advanced manufacturing planning. We want to emphasize planning for the future. In engineering, we should always be thinking not just about what we're doing now, but what are we going to be doing next? Because what we do now sets up what we're going to be doing next. So this is slightly different from our process planning, because we're thinking about what are we going to be making on a long-term basis, rather than what we're making now and how we're going to sell that. So when we think of advanced manufacturing planning, we're trying to forecast what new products will be introduced in 2 to 10 year time frame, and to determine what are the production resources that we'll need to make those future products. So some of the things we do in advanced manufacturing planning: one is we evaluate new technology. We need to look at new technology and make the decisions whether we're going to develop these new processes for our future products, or are we going to purchase things made with these new technologies from vendors. We need investment product management. What are the investments that are going to be required for these new process technologies? We have to plan for those and manage those. We have to introduce facility planning. Are we going to need new facilities to produce new products, or are we going to be able to change over the facilities that we have now? We need manufacturing research and development to develop our new process technologies. We may not invent the new process technologies, but we have to experiment with them to know how to use them effectively. All right, so here we have a flow chart kind of showing how they envision using the advanced manufacturing planning. So we're doing manufacturing research and investment project management on what are we going to be using in the future. That goes along with our facilities planning and our new technology evaluation. That all goes into our advanced manufacturing planning. We're going to be investing in the new technologies and facilities needed that will enhance our existing manufacturing capabilities and help shape our future manufacturing capabilities. All of this goes into our new product ideas, but also helps us on what are our future products going to look like. So this becomes a never-ending loop around here that is fed by our advanced manufacturing planning. Okay, well, once again, I have to remind you, this work is copyright. Do not even think about stealing it. Are there any questions? This is your chance, guys. Ask some questions. No? A person? No. Okay, well, so much for the use of chat for good communication back and forth. Okay,
Can I ask a question?
of course.
What's the difference between a design and manufacturing engineer?
Well, theoretically, a person could be both of those. If we have a small company, the same person that designs something may be the manufacturing engineer. But if we're talking a large company like Boeing or Ford or GM, they're going to have a design division and a manufacturing division, and so on. So usually design engineers will be mechanical engineers or electrical engineers, or they may even be just pure designers that don't think about the engineering, they just worry about the form. Where manufacturing engineers tend to be people that have specific manufacturing engineering or industrial engineering training. Okay, good question. Any other questions? Okay, well, I'm going to call that no questions, and have fun, have a safe weekend, and I will see, I'm making bunny ears with my fingers, see you on Monday.
How many students do you have?
One. And she's in quarantine.
What class is this?